measures integration and analysis class. The last sessions of the previous chapters we discussed several deficiencies of Riemann integration. So it's to remedy those deficiencies. So in this chapter we extend the notion of the length of intervals to a larger collection of subsets of R, and this leads us to measures, and then the next chapter to integration with respect to measures. So we are going to begin this chapter by investigating outer measure, and then which actually look nice, but as long on we see that it actually fits some crucial properties, and then we also see how we're able to remedy that. So the first part we are going to cover in this measure is outer measure on R. So let's call this section 2A. Outer measure on R. So the Riemann integral arises from approximating the area under the graph of a function by sums of the areas of approximating rectangles. But now we want to see, is there a way whereby we can just, instead of going along with partition, then can we just go to extend our to find the integrations of a function rather than by partitions of rectangles? Then we can just go by length, extending our size, so using the word length of each set. So that's why we first of all tried to discuss when we begin the expected definitions of length of an open interval, and then from there we are going to go to the definition of outer measure properly. So the first definition: we have length of open interval Li. So the length Li of an open interval I is defined by L1 equals to we have B minus A if I equals to open interval A comma B for some A comma B that belong to R with A less than B, and then 0 if I equals to empty, and then infinity if I equals to open interval minus infinity A, or I equals to A comma infinity for some A that belongs to R. And then lastly we have infinity if I equals to minus infinity comma infinity. So suppose A is subset of R, so then we can now try to define what a outer measure is going to be. So that leads us to definition 2.2. Outer measure A. So the outer measure A of a set is subset of R is defined by we have outer measure of A equals to infimum K equals to 1 to infinity and on K such that I1, I2 that are open cover, open intervals such that they cover A. So the idea of it is that the size of A should be at most the sum of the length of a sequence of open intervals whose union contain A. Then taking the infimum of all such sums gives a reasonable definition of the size of A. So for an example, if we have this is our A, then we can get some open interval then we can get some open interval, that is, we can call that to be I1, I2, I3, I4, I5. So it's not necessary that they are disjoint, there can be an overlap, but the main point is that these our I's must cover the whole of A. Then we know that the length of all these I's must, and we take the infimum over all these our possible open intervals, then that should give us the size of A. Okay, so that is just the basic idea. So with that, we need to take note of some things which should be up for us. So note the definition of outer measure involves an infinite sum. So then the infinite sum is summation k equals to 1 to infinity of tk of a sequence t1, t2 ... of elements of 0, infinity is defined to be infinity if sum tk equals to infinity. So, and then otherwise, the summation k equals to 1 to infinity tk is defined to be the limit of increasing sequence. T1, T2, T3, ... T1, T1 plus T2, ... dot dot dot. So then of partial sum, and that we have the definitions of our partial sum. K equals to 1 to infinity of tk can be written as limit n tends to infinity, that's k equals to 1 to n. So we can first of all take the partial sum, then take the limit, then we have the sum, the infinite sum as our definition. So let's take some examples and then get their outer measure. So let's call this to be 2.3 example. We have finite set as have outer measure 0. So let's say suppose A equals to A1 dot dot AN. So this is a finite set because this is AN. So it's a finite set of real numbers. So suppose epsilon is greater than 0. So we can define a sequence of open interval I1, I2 dot 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 of open intervals by, so in other words, wants to cover the whole of A with this our open interval. So IK equals to AK minus epsilon, AK plus epsilon. So this is if K is greater than or equals to N, and it will be empty if our K, so this can less than if our K is not greater than N, because we are already considering the finite set. So you can see vividly that this our the sequence of this open interval actually covers our set A. Is a sequence of open intervals whose unions contains A. So then if we, for example, for illustration, we have something like this. Let's have something like this. So assume that this is just one of the points. So we have our A to be A1, A2, A3 dot dot dot. So then we can now find some open intervals, which we can just take like this point, and then this can be A1 minus epsilon, and this can be A1 plus epsilon. So then we continue like that and cover the whole of A. So you will see that so obviously you will know that the summation of our length, let's first of all calculate the length of IKs for all k equals to infinity. That will just be AK plus epsilon minus AK plus epsilon, and that is equals to 2 epsilon. This for each case, for each k, and then we have n numbers of k. Okay, that is summation of k equals to 1 to infinity L of 1k will be equals to 2, because we have n numbers of k and others are empty, so we should be 0. Then we have this result. So if we now take the infimum, hence the outer measure of A is always less than or equals to 2, less than or equals to summation of k equals to 1 to infinity length of ik, and that is equals to 2 xn n. So since xn is an arbitrary positive number, since xn is an arbitrary positive number, so this implies that the outer measure of A equals to 0. Okay, so take note of that means that the outer measure, finite set have outer measure of 0, because it's not and that appeal intuitively that you cannot measure a single point. If you have a you want to just mention this single point, so that does not actually make sense, right? So if you have many points, so you want to measure the length of this point alone, 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 so you actually have 0. Okay, so let's check some good properties of outer measure. Properties of outer measure. So our outer measure has several nice properties that we are going to discuss in these sessions, and we begin with a result that improves upon the sample we did above. So the first properties got 2.4, countable set, have outer measure 0, so that means every countable subset of R as outer measure 0. So let's check the proof. Very nice proof and very it's an easy one. Proof. Now suppose A equals to A1, A2, so it's a countable subset of R. So let epsilon greater than 0. So for positive k, so we can define our sequence of open interval for each of k's to be ak minus epsilon over 2k, comma ak plus epsilon over 2k. Then you see that this is a sequence of an open interval of open interval whose union contains A. So then if you take the length of these guys, just like previous one. AK plus xnum over 2k minus AK plus xnum over 2k. Then you're going to have 2 xnum over 2 raised to power. Okay, so that's for each case. So then the summation of k equals to 1 to infinity of 2 xnum over 2k. That will be equals to 2 xnum summation over k equals to 1 to infinity 1 over 2k. And this is a geometric series, and that is equals to 1. So since that's equals to that, so we have our outer measure of A to be less than or equals to 2 xnum. So because xnum is an arbitrary positive number, is an arbitrary positive number, so this implies that the outer measure of A is equal to 0. So the result above also allow us to show that the outer measure of irrational numbers, which is countable, also has outer measure 0. Note Q, irrational number, is countable, thus the outer measure of Q equals to 0. So then the next result, which is also a nice property that we need to take note, under which I got 2.5. We have outer measure, preserve orders. Okay, so suppose A and B are subset of R with A subset of B, then the outer measure of A should be less than or equals to the outer measure of B. So this is also a nice proof. This also have a nice proof. So the first thing is to define a sequence of open interval that actually cover whose union contains B. So if the union contains B, then the union also should contain A, right? Then the union of the sequence of open intervals also contain A. So in other words, the outer measure of A will be less than or equals to the summation of k equals to 1 to infinity of the length of those sequence of open intervals that contain B. So taking the infimum over all sequence of open interval sequences of open intervals that contain whose union contain B. instance b. So we have, but that will be the definition of this guy. So that gives us the outer measure of B. So thus, outer measure of A is less than outer measure of B, which is a nice property. So another thing is that we expect the size of a subset of R should not change if the set is shifted to the right or to the left. For example, intuitively what I mean is that if we have from here to here, let's say this place is 2, 4. Okay, so then the length of this, the size of this closed interval is just 2. So if we shift it just a little bit, maybe just shift it by 1, then we have this place to be 3, this place to be 5. Then the length also should still be the same. And if we shift it by reducing it from 1, we shift it to this point, we have 1, we have 3, then the size should remain the same. So, and that is what we are going to do with. First, we have to define what a translation is. 2.6 definition. We have translation. Now that was just a shifting of T plus A. So we have if T belongs to R and then A is a subset of R, and then the translation T plus A is defined by T plus A equals to T plus A such that A belongs to A. So we also have to introduce translations into our outer measure. Okay, and that we are going to divide that to be 2.7. The outer measure also is translation invariant. So suppose T belongs to R and then A is a subset of R, and then the outer measure of T to A should also just be the outer measure of A. So let's share the proof. So first of all, in this sequence, don't forget that suppose I1, I2 is a sequence of open interval whose union contain A contains A. Then if we translate it, then T plus I1 T plus I2 dot will be a sequence of open interval also whose union we also contains t plus a. So thus the outer measure of t plus a will be less than or equals to the length of k equals to 1 to infinity length of t plus a, and then this is just equals to k equals to 1 to n length, sorry, this ik, length of ik. And since ik is open intervals that contains a, then taking the infimum of the last terms over all sequences I1, I2 of open intervals which do not contain a, so we have our outer measure of a to be less than the outer measure of a. So to prove the other side, so to get the inequality in the other direction, so we just note that a equals to minus t into bracket t plus t plus a. So the trick is that we can just apply the previous paragraph by first of all taking this all as a. If you replace this as a, then take the sequence of open interval that cover this, then we take this translate invariant with this, then we can define a sequence of open intervals that cover all this. Then if you follow suit from the previous step, then it's going to see that the outer measure of a will be equal to the outer measure of minus t plus a less than the outer measure of t plus a, because we have taken this to be, we take this to be a, okay? Then we first of all find the sequence of open intervals that contain this, then take this as a translate invariant, that minus t plus, maybe if we choose j case to be the open intervals that contain this guy, then you cannot define, let me use another notation so that you don't mix it up. So if you take j case to be an open intervals, j equals to 1 to infinity to be an open intervals that contain a, then we cannot define another open intervals which we can call jk minus t plus jk, and this also will cover the whole of minus t, all of these guys. Then if you follow the same procedure, then you get this desired results. So by this direction and in this direction, we can conclude that the outer measure of t plus a is equal to the outer measure of a, and that ends the proof. A nice one. Okay, all right, let's check one more properties, which is a very nice one and good one to prove. And it got us 2.8. Countable, subadditivity, of outer measure. Okay, suppose A1, A2 dot is a sequence of subsets of R. Then we have this theorem, union of A case k equals to 1 to infinity. The outer measure of this guy is less than the outer measure of individual. So let's check the proof. So first, if ak equals to infinity for some k which is positive integer, then the inequality will hold, right? Because this left hand side will either be equals to infinity or less than infinity. Okay, and if one of these guys is infinity, the summation of any number with infinity will also equals to infinity. So we have to make the assumption that the outer measure of k is less than infinity for all positive k's. Okay, so now let's now define a sequence of open intervals that can cover this guy. So let I1 comma k comma I2 comma k, because we are dealing with sequence of subsets. We are not only dealing with 1a, so that's why we have this k. So I1k comma I2k comma I3 comma k dot be a sequence of open intervals whose union contains ak. So if the union contains ak's, then we can select epsilon greater than 0. Then for this, each ak's whose union contain a, then the outer measure of ak will now be greater than the length of those guys whose union contain ak's. Okay, so if you have any question, you can drop it at the comment section. So then if we now take the summation over all k equals to 1 to infinity, equals to 1 to infinity ak plus k equals to 1 epsilon over 2k. So obviously you know that this guy is a geometric series that will be equals to epsilon. So then we can rewrite it as summation k equals to 1 to infinity g equals to 1 to infinity the length of I jk is less than or equals to epsilon over k equals to 1 to infinity the outer measure of each case plus epsilon. Okay, so now this double indexed collection of open interval, we can rearrange it in such a way that the sequence of open interval whose union is going to contain the countable union of these guys. So rearrange the double indexed collection of open intervals IJK such that the union of those guys is going to, let's complete it into a sequence of open intervals whose union we contain u k equals to 1 to infinity 18. So that means that our UK UAK k equals to 1 to infinity is a subset of U of length of subset of IJ comma K. Okay, guys, J equals to 1 to infinity, K equals to 1 to infinity. So if that holds, that means that we can now substitute this at this point. So with that, we have our union AK K equals to 1 to infinity. The outer measure is less than or equals to what we have at this right hand side. Summation K equals to 1 to infinity outer measure of AK plus epsilon. And that is that. So what we just did is that we rearrange this sequence, this double index collection of open interval, as a sequence of an open interval such that they contain this guy. So if they contain this guy, then the outer measure of this guy will be less than or equals to that guy. So since epsilon is an arbitrary number, then we have this K equals to 1 to infinity AK is less than or equals to the summation of the outer measure of each case. So that's what. So that means what? Not that the countable addivities implies A1 union A2 union A3, that's union AN will be less than or equal to the outer measure of individual, which is actually a nice property. So, and then if you look at this example, if you have 3, here let's say we have 3, 4, 3, 5, 4, 6. So if you will see that, let's call this You see that 3,5 union 4,6. That will give you 3,6. Okay, so if you find the outer measure individually, the outer measure of this, the size of this is 2. Then plus the size of this is also 2. And that gives you 4. But that is not equal to the size of this, which is just 3. So you can see that the outer measure of the individual is actually greater than the outer measure of the union. So that is what we mean by countable subadditivity of outer measure. Here we stop. So next time we are going to check outer measure of closed bounded interval. Hope to see you in the next video.